Hello, I'm Jiyoung, and today we'll be talking about our project, accelerating the action expert in SmolVLA using ALLO on FPGA. And this is group work with Hyun, Wei, and Ivan for ECE6775. This is a high-level picture of SmolVLA. So SmolVLA is a vision language action model, which takes in multimodal inputs such as images, video, text instructions, and the robot's own sensory motor states. And then these go into SmolVLM2, which is a vision language backbone that encodes everything into a compact feature representation. Then these features are passed into the action expert, which is also a transformer. And on each forward pass, it produces an action chunk, which is a sequence of 50 time steps of continuous control vectors that map to actual robotic actions. Yeah. So motivation for why we chose to accelerate the action expert of the small VLA. So small VLA is intentionally small compared to other VLA models and it has far fewer parameters, which means we're not trying to cram like a huge billion parameter model into the FPGA. And this also means that the model is feasible to actually generate the bit stream and then run it on the FPGA. And our overall goal is to leverage these properties, like this property, to build a high throughput FPGA inference engine for the Action Expert using the ALLO DSL framework and then validate it against software baselines to show that we can get increase in performance without losing functionality. Yeah. So why did we choose ALLO and FPGA? So on the hardware side, FPGAs are a natural fit for these kernels because we could build deep data flow pipelines, keep the KQV tiles on chip, stream data to avoid round trips to external memory, and also DSP blocks map nicely to the floating point operations in the Action Expert, and the deterministic pipelines of the Action Expert also map well to the FPGA. And on the software side, ALLO gives us an MLIR-based DSL that's specialized in building accelerators versus Vitis, which is more general purpose. And we're also recommended to use ALLO over Vitis HLS for our project by Professor Shane. Yeah. So the expert, so zooming into the action expert architecture, it's a flow matching transformer. And instead of models like GPT, which auto-regressively predict one token after the other, it starts from 50 noisy action tokens and then iteratively refines the whole 50-step trajectory um, through each layer. So each layer predicts a kind of velocity vector that nudges these noisy action tokens towards a more meaningful trajectory. And architecturally, the Action Expert has 16 total layers, and each layer consists of a layer norm, one of the two attention mechanisms, uh, residual, layer norm, and then an NLP. And additionally, the Action Expert uses this interleaving mechanism between self and cross attention, and its purpose will be discussed in the next few slides.
So on this slide, I will talk about the self-attention kernel we implemented in ALLO. Self-attention lets each token look back at all earlier tokens and decide which one matters, essentially performing a weighted average. We project the input into queries, keys, and values, compute similarity scores between Q and K, apply softmax to turn those scores into weights, and then use those weights to blend the values. In our setup, we're operating on 50 tokens with a head dimension of 64, and we use group query attention with a group size of 3. Instead of giving every query head its own K and B, GQA lets multiple Q heads share the same KV head, which significantly reduces memory traffic and is much more hardware efficient. And as shown in the diagram here, the kernel includes the projection gems that generate Q, K, and V. Lobes is then applied to both Q and K to add more positional information. And each KV head processes a small group of Q head, and the mask QKT gem enforces causal masking, so token I never attends future tokens. And finally, the softmax times V gem and fuse accumulation right out the result of the final buffer.
While self-attention let action token reference their own history, cross-attention let those tokens attend to the VLM encoder feature, which provides the visual and language content needed for the action generation. Shown in the diagram, Q still comes from the action sequence, but K and V come from the VLM encoder feature. We still apply row and ground query attentions, but now the KV represents multi-model content rather than past action. From a hardware perspective, this is great because the VLM-KV feature are fixed for a whole chunk. We can load and stream them once, cache them, and then reuse them. However, despite having a complete CA baseline implementation, we did not optimize course attention. due to time constraint and limitation in the current ALLO toolchain, we focus on our optimization efforts on self-attention and the MLP, which offer cleaner performance leverage and fewer kernel-specific constraints. Yeah. On this slide, I want to highlight how self-attention and cross-attention align structurally and why that matters for our hardware design. Even though the two mechanisms serve different roles, self-attention model relationships within the action sequence, while coarse attentions inject external context, the computation they perform are almost identical. Because the core loop structure is the same, we design both kernel using a shared ALLO template. This is a greatly simplified development, and this matching is exactly what we make the entire action expert feasible to accelerate as a coherent hardware pipeline.
And on this side, we'll talk about the MLP block that we implemented in ALLO. While attention mixes information across tokens, the MLP processes each token independently and expands the hidden dimension to a much larger dimension before projecting it back down. And as shown in the diagram here, we take the input state X and apply two linear projections in parallel, a gate projection and the output projection. The gate projection then goes to a serial activation which acts like a learn gate. We then multiply the activated gate element-wise with the up projection. This produces a filter version of the intermediate tensor that passes through a final down projection to return to the model's hidden dimension.
We were guided by Professor Giro after we had implemented these baselines of all these kernels to to do an operational intensity analysis of the kernels. The goal is simple. We wanted to identify the kernels which dominated the total operation count and therefore deserve the most optimization effort. From the OI analysis, as seen on the screen, we see the MLP accounts for roughly 4 times more total operations than the self-attention. When we later profiled the code, we found that the same ratio reflected in actual runtime. We also computed both the best case and worst case memory operation, total number of memory operation. Worst case reflects our initial implementation with its limited data reuse, and best case assumes every element is loaded once. In the best case scenario, the MLP and self-attention layers have an OI, have the same OI. This is because both are dominated by the matrix multiplication, so it makes sense. Since MLP clearly dominates the operation count, we focus our initial optimization efforts there. Breaking down the MLP's kernels, we see that the linear layer, which as mentioned previously is a gem kernel, are the costliest kernels, taking up a few orders of magnitude more operations than the others. This motivates us to focus our initial round of optimizations to improving the MLP's linear kernels. We see the same pattern in the attention kernel where gem projection kernel, as seen at the bottom of the list, is again dominating the total number of operations, and also these kernels have the largest room for improvement in theoretical OI. So that is again where we focus the main brunt of our initial optimizations.
Yeah, so given those analysis, here's what we implemented. For the MLP and attention, we've used multiple kernels. For example, combining separate matmos and bias add stages in order to eliminate redundant intermediate buffers between the kernels. And this reduced memory traffic and improved latency significantly. And we'll talk more about this in a future slide. For retention, we focus first on gem optimizations, as our OI analysis revealed that there is the greatest potential for optimization in the gem. And to do this, we restructured loops, added pipeline, and unrolled pragmas in order to essentially increase the number of floating point operations running in parallel. We also explored more aggressive ideas like systolic arrays for gems and some tiling strategies, but as will be mentioned in the future slides, some of them were blocked by the tool or time limitations. We also looked into theoretically quantizing the float 32 weights down to N8, and which we'll also talk about more in the future slide.
And so finally, to measure the effectiveness of our optimizations, which was previously discussed, we performed both analysis from the CSynth and bitstream generated from our implementation. As seen in the table, all our optimizations to both MLP and attention brought 2x speed up over the baseline. Note these results are done using 4.32 precision due to a bug in ALLO preventing the use of lower precision floats for some critical malfunctions. We test these gains to the optimization previously mentioned. We also want to quantify the effectiveness of quantizing on the overall performance. As seen on the slide, we gain a 5x speed improvement when using int8 quantization on top of our optimizations. However, when we looked at the area usage on the U280, we found that none of the implementations fit on the FPGA. Even the Int8 implementation fails to build during placement for making the bitstream. The issue comes from a current implementation in ALLO where every kernel must load all of its weights from onboard HBM into BRAM at launch of the kernel. Our model is simply too large to fit in the HBM to generate a working bitstream. To generate a working bitstream, we reduce the model dimensions so that the 4.832 parameters will fit in the FPGA. And as seen here, the speed up is lower than what was observed in the full model, both in the CSIMF and the estimated FPGA. Though it's worth noting that the estimated and measured speedups are still matched closely. We believe the reduced speedup comes from a smaller model dimension. Once the dimension shrinks, the OI-based optimizations in our gem kernel are less effective, which reduce the benefits of the optimization strategy we had originally applied. We believe the results from this section can further be improved by doing more extensive gem optimizations, like, for example, using systolic arrays, tiling, and dynamic loading. So, for example, loading the entire model again. But due to both time constraints and constraints we ran with ALLO, we leave this for future work. As part of this project, we have thus far submitted 2 bug reports to ALLO, and we'll post another one for bugs we ran into. We hope this will help ALLO's ecosystem by getting these issues fixed so more people can use the system. Here's a demo of the full layer running on a Levo U280 FPGA. On the right, you see the code loading up on the FPGA, and on the left, you see the HLS code that was generated on ALLO and the bitstream is based on. As you see right now, it's learning, and there we go, it's already finished. And as we see, we have around a 0.08 second runtime.
Yeah, and a big shout out to Professor John throughout the semester for all the support, and a special thanks to Nianson for all the support for the final project and for all the labs as well. And yeah, thank you.
Thank you.